Hello, everyone, and welcome to session 1 of Getting Started with Perception ePower. In this session, we will be reviewing how to configure hardware and doing just a general introduction to perception. My name is Krista Tweed. I'm an applications engineer with HBK. When you first start perception and connect to a power analyzer, your screen will look something like this. So you are automatically opened in the ePower Suite sheet, as we call them. The first step in configuring your setup will be to select the right starting point. So if you go to the ePower Suite menu and select ePower Suite application, a dialog is going to open that will show you a variety of options as a starting point. The idea here is just to get as close as possible to your configuration, your hardware configuration, and you can change it from there. So the eDrive tab has options for power source, inverter, and an electric machine. The basic tab has options for just doing a mains measurement or just a machine measurement. And the e-axle tab has options for different types of axle measurements. I'm going to stay with the basic driveline setup, which won't change anything. And we'll look at how to make measurements or set up a measurement for both a single phase and 3-phase power source, as well as an electric machine. So each of these components here, what we pre-configure is a power source component with an output connector, an inverter component with an output connector, and a motor component with an output connector. If I double click on that output connector, then the setup panel for that option slides open from the left side. I have a measurement enabled. You can see at the top a drop-down list for the types of measurements that you might make on each connector. I'm going to leave this one on a DC 1-phase measurement. Once you've selected the measurement type, you can click the drop-down for which channels where you want that measurement made. I'm also going to select the default from that. Here, when you see the first letter that's in the channel names, it tells you a recorder or a slot label. So in a GenDAC mainframe, the slots are labeled by letters A, B, C, D, and we refer to them in perception as recorders. Recorder A is in slot A, recorder B is in slot B. And then the channels are given names based on that. In my case, in slot B, I have a GN310 power module. So that module has 3 voltage channels and 3 current channels. So the default channel names are U1, U2, U3 for the voltage channels, and I1, I2, I3 for the current channels. Since I'm doing a single 1-phase measurement, I will just select U1 and I1 as my voltage and current channel for those measurements. The next important step is to come down to the current transducer entry and select what current transducer is sitting in front of the current channel. For the purposes of this demonstration, I'm going to just select one of the current transformers from that HBM cells. So I'll select the 200 ID. Once I've selected that current transducer, now perception knows how to convert the current it's seeing on that channel into, or convert the current into the actual physical measurement that it's seeing. And now I need to go up into the span area and select the maximum input range that I expect to use for both my currents and my voltages. All of the power modules built by HBK offer a variety of what we call spans or amplifier ranges. You want to select the span that most closely matches the measurement you expect to make so that you can get the maximum resolution out of your measurement, because the 18 bits of this digitizer will be placed across the measurement span that you select. In my case, I don't expect to go above a 70 amp peak measurement. For that reason, I'm going to select the 150 amp span. That's a bipolar span, so it's plus minus 75 amps. You can see we also list the RMS value in parentheses because many people who do power measurements think in RMS rather than peak. So I'll select that 150. On the voltage side, I don't need a transducer in front of my channel because these voltage channels support up to plus minus 1500 volts in directly. I don't expect to be measuring above a 500 volt peak for my DC power input, so I'm just going to select that 1 kV span and leave it there. For cycle detector settings, I'm going to wait and discuss that as we set up the inverter channel. So that's all we need to do for my DC power measurement. I now come over and click on the inverter component. Now I can set up that measurement for my 3-phase power. You can see in the drop down the list that you're able to measure those 3 phases any way you like: phase to ground, phase to neutral, phase to phase. I'm going to leave it with phase to artificial star, 3-phase, phase to artificial star, because that's what I have. I'm again selecting the channels that I want to use for the measurement. Perception shows me what channels are available in my mainframe. In this case, I have a GN610B power module in slot A. That input module supports all voltage measurements. So you see here the channels A1 to A6 are how those channels are default named. Again, I'm going to select my current transducer from the sensor database. I'll go to that span, and I'm going to increase because I expect a slightly higher voltage on my inverter. Now for the cycle detector settings, cycle detect is a unique feature of the HBK power analyzer. Because of that, I want to take just a few minutes to go through the basics of the cycle detect. It's an important feature of how the power analyzer works. So I'm going to go over to PowerPoint here. A traditional power analyzer uses a phase lock loop to synchronize with the input signal, and that phase lock loop, or PLL, requires a bit of time to synchronize. In our case, we take a different approach because we wanted to be able to provide power results in more of a dynamic way. So what we do is the user specifies a cycle source. It's typically the first phase of current. And we're going to filter that signal for cycle detect purposes only, and then do level crossing searches to determine the cycles over which we want to make a measurement. So you can see here a typical sine wave. We're looking for, say, a 0 level crossing in a positive direction. When you find consecutive 0 crossings in a positive direction, you've defined the cycles over which you want to make a measurement. The user gets to decide if they want to make measurements over half cycles or integer numbers of cycles, anywhere from 1 to 50. The fewer cycles you use for your averaging, the more dynamic your power results will be. You'll get a result more quickly. The more cycles you use for your calculation will improve the accuracy. You're averaging over a longer time period, but you'll have a less dynamic result. So for the cycle detector settings, you're going to determine the channel that you want to use as the cycle source, the number of cycles that you want used for calculations, and the level that we will search for to determine those cycles. Typically that is 0, and we use that as the default. But if you have something more unusual like trapezoidal current, then you could set that to something, a value other than 0. We have several tools that allow you to optimize your cycle detect. The first of those is hysteresis. So what hysteresis does is you set a hysteresis value, and that creates a hysteresis band below the level that you're searching for. You want the hysteresis to be larger than the noise within your signal, but smaller than the signal itself. So this graphic shows you if the signal comes into the hysteresis band and exits it without crossing the level of interest, that's not a valid level crossing. You have to come from below the band and cross into the hysteresis band and across the level to get that valid cycle or that valid level crossing. We also have you specify the maximum fundamental frequency that's expected for the cycle source, and we use that frequency in 2 different ways to optimize the cycle detect. It sets the cutoff frequency of the cycle source filter, so we filter the signal to remove some of the noise, but it also defines a cycle detector hold-off time, meaning that we don't look for another level crossing until at least that half cycle period of time has passed. So here's an example of what comes out of the cycle detect process. What you're seeing here in a perception display is the current sine wave, and then this cycle master signal is the output of the cycle detect. And so you're always able to view that square wave and see what cycles were detected. Now in this case, I'm looking at the I1 channel non-filtered, so you can see that there's a slight phase shift for that cycle master. That's expected because filtering that signal will always end up causing a phase shift, but it's not going to affect any of the power calculations because we're still making those calculations over an even number of cycles. We also provide a cycle check signal. What we do is find the frequency of that cycle master signal, and you would expect then that cycle check frequency is going to have the same shape as your speed. The exact value won't plot the same due to number of pole pairs and possibly a slip value, but the shape should be the same. If you see spikes in your cycle check signal, those are telling you that's a place where the cycle detect either detected too many cycles or missed detecting some cycles. And you can go in and look at your signals in perception and understand what's happened to cause that. The other option we offer is doing calculations on a fixed time interval. So you can choose from the values shown here, 1 millisecond, 10 milliseconds, 50 milliseconds, etc. And in that case, it's literally just the calculation done over that fixed time period, and then a new calculation starts. All right, so if we look at how we set that up in ePower Suite, we've got this cycle detector settings area. We set the channel that we want to use as the cycle source. So we're either going to use a current channel, a voltage channel, choose the timed option, or we can also link the cycle detect to another component and use the same cycle detect as that other component. We set the number of cycles we want to use for the measurement, the level we want to use, and then the hysteresis and the max fundamental frequency. I do recommend leaving the hysteresis on a dynamic option. We have a static option, but the nice thing about dynamic is that it's going to set the hysteresis to be a fixed percentage of the current span of the channel. And so as you may change what span you're operating on, you don't have to worry about going and adjusting your hysteresis measurement as that changes. I also recommend keeping this checkbox active for the auto-timed mode. What this does is let the user, if we do not detect a level crossing within 1 second, then we're just going to provide a calculation result over the most recent 1 second of data. That means when your machine may be just starting up and the current is not completely there yet, enough to get a valid cycle detect, you will still get some power results out. Now, if I go back to my power source for a moment, you're going to see that I've linked the power source cycle detect to my inverter out. And especially when people are interested in efficiency type measurements, that's the most common selection. They want the efficiency, the parameters that go into the efficiency measurement to all be made over the same time scale. And therefore you want the cycle detect of all of the components involved in that efficiency measurement to be the same. So we will just link that to the inverter out. On the motor side, if I click on that component, you can see we offer a variety of mechanical options. You can measure torque and speed either in an analog or a digital way. In this case, I'm making a digital torque and speed measurement from an HBM torque transducer. I'm going to select that transducer. I've got a T40B with a 60 kilohertz center frequency. And on the speed transducer, I will select the same thing. You want to be sure any sensor in the sensor database that has RPM in the name is the speed sensor that's part of that torque transducer. So I'll apply that to my speed channel, and I can enter my maximum expected torque and speed values. So I'll have 50 Newton meters as my max torque, and we'll leave 1000 RPM for my speed. And again, in the cycle detector settings, I'm going to link that to my inverter out so that I have a torque measurement, a torque and speed mechanical power measurement over the same cycle detect as my electrical, my inverter measurement. And the only type of component we haven't discussed setting up yet is the inverter or the efficiency component. So in this case, I've selected the inverter efficiency. You have an option for efficiency measurements of making it either an input to output, output to input, or both directions. We have many users who, depending on what tests they're running or how they're doing the test, sometimes they're motoring, sometimes they're generating. So they're interested in setting up efficiency for both directions. In my case, I will always be motoring, so I'm just going to set up that efficiency from the input to the output. And I select that my input is the power source, and my output is the inverter output for that efficiency. If I click anywhere outside of the components, then that setup panel closes. Now you can see here, it's also very easy to add additional components. So if I click on an Add Component button and then double click on what I've opened, you can give that component a name. Let's just say for a moment that I'm actually have a dual inverter type setup. So I'm going to call this Inverter 2, and I'm going to add an input connector and an output connector for that inverter. When I click on the input connector, I'm not going to make a measurement there, so I'm going to check the box to disable the measurement. And I'm not going to actually set up a measurement there at the moment. I'm just going to close it. But if I wanted to just show you moving some of these things around, let me move my efficiency boxes out of the way. And I'm going to move my inverter here. And now I could set up my power source to add a connection to go to the inverter 2 input as well. So you can really build up a nice graphical picture of how your interface works and what measurements you need to make. Now, once you've configured all of those measurements, of course, you also have to wire everything up. And Perception offers a nice option under the ePower Suite menu for a channel assignment list. So I can click on that and I can either sort it by mainframe connection, the various components, or meaning the inverter and the motor, or per connector. So whichever way is easiest, you believe, for the people who will be wiring up the system, then you can provide that channel assignment list to them. Now, when I have all of my hardware settings in place, I want to go ahead and save a virtual workbench. So I'm going to go to the File menu, select Save Virtual Workbench As, and I can call this And now the next time I come back to Perception, I can open up that virtual workbench file and come right back to this location without having to do all of that configuration work again. I think that brings us to the end of session 1 of Getting Started with Perception ePower.